Imagine yourself sitting in a completely dark room, with only the faint glow from your computer screen casting light onto your face. The air around you feels chilly and enveloping, and somewhere in the background, the soft whirring sound of the computer fan hums steadily, reminiscent of wind blowing through the vast expanse of outer space. Outside the window, the night sky appears pitch black, devoid of even a single star, and a heavy silence prevails, making you acutely aware of the profound loneliness that permeates the universe. However, as artificial eyes, those enormous telescopes such as the James Webb Space Telescope or the Hubble Space Telescope become increasingly advanced, they start to paint a more vivid picture than ever before. Light traveling from distances billions of light-years away floods in, carrying images of more than 2 trillion galaxies that humanity has discovered so far, according to the latest data from cosmic observation missions in the year 2025. These galaxies sparkle like clusters of diamonds scattered across an endless darkness, and no force can stop us from exploring even further. The universe has existed for nearly 14 billion years, based on precise estimates from the updated Lambda-CDM model informed by Planck mission data and recent observations, and the stars continue to shine brilliantly without a single moment of dimming. Yet, space remains strangely dark. Have you ever wondered why? Picture this scene: the universe as a vast, dark ocean, boundless and immense, where light from billions of stars struggles to spread but falls short of filling the enormous voids. The reason is both simple and profound: stars do not last forever. They are born from gigantic clouds of gas, burn brightly for millions or billions of years, and then fade away in dazzling explosions or quiet contractions. Their lifespans vary greatly. Some are as brief as a flash of lightning, while others endure like an endless river. Moreover, the universe is expanding at an accelerating rate, as revealed by discoveries about dark energy from recent observations of Type Ia supernovae. Light from distant stars does not have time to illuminate the entire expanse before those stars exhaust their lives, leaving behind dark emptiness. Nothing is eternal. The moment a star is born, a countdown begins, much like human life, where some exist quietly, passing gently like falling autumn leaves, while others live vibrantly, brilliantly, and depart with pride amid echoing resonance. Astronomers, through detailed studies from space telescopes, believe the first stars formed roughly 100 million to 250 million years after the Big Bang. This marked the end of the prolonged dark ages of the universe, transitioning into an era of light. Envision the early universe as an endless night sky without a glimmer of light, filled only with evenly distributed hydrogen and helium gas. Then, suddenly, gas clouds began to collapse, and the first stars ignited, bringing the initial light that banished the darkness. Today, we inhabit a universe teeming with luminous objects, where stars are the most common celestial bodies, massive spheres of plasma that dominate, with hundreds of billions in the Milky Way alone, according to updated estimates from the Gaia mission in the year 2025. Recent analyses from Gaia have refined this to approximately 400 billion stars in our galaxy, highlighting the sheer scale and diversity. But are the stars we see today identical to those first-generation stars after the Big Bang? To answer this, we must return to the Dark Ages, a period lacking direct observations. Scientists measure the redshift of light from the most distant objects, such as quasars or ancient galaxies, to infer the past. The early universe was uniform in energy and matter density, without light sources to disturb it, smooth like a calm lake surface under a quiet night sky. As the universe expanded, temperatures dropped from billions of degrees to just a few degrees Kelvin, densities decreased, and uniformity broke. Ordinary matter and dark matter began clustering into separate regions, forming the foundations of large-scale cosmic structures like the cosmic web we observe today through supercomputer simulations. Advanced models, including those from the Illustris TNG project, simulate this web with filaments, walls, and voids spanning hundreds of millions of light-years, connecting galaxy clusters in an intricate network. The cause of this breakdown in uniformity remains uncertain in science, but it may stem from tiny quantum fluctuations during the inflation period immediately after the Big Bang, akin to a single drop of water falling onto a still pond, creating ripples that spread and lead to the dynamic universe we know. During that phase, the universe contained only pure hydrogen and helium, in a ratio of 3/4 hydrogen and 1/4 helium from Big Bang nucleosynthesis. Under those conditions, star formation was easier than today because heavy elements were absent to hinder the process. Temperature was key. It had to cool sufficiently for matter to clump, separating from dark matter. Primordial clouds, enormous in size, collapsed under gravity, core temperatures rising to about 1000 Kelvin, where hydrogen atoms bonded into H2 molecules, emitting infrared radiation that cooled the cloud to 200 to 300 Kelvin, reducing pressure and promoting further contraction. The cloud spun like a miniature galaxy, accumulating mass until a threshold was reached, then collapsing into a star. In contrast, modern star-forming clouds contain heavy elements, metals from the remnants of ancient stars, cooling easily to 10 Kelvin. With pure hydrogen, cooling below 200 Kelvin was impossible, so the first stars required temperatures 20 to 30 times higher and masses 500 to 1000 times that of the Sun. Abundant hydrogen and helium allowed them to grow gigantic, lasting only a few million years before collapsing into supermassive black holes, powering quasars and becoming galaxy centers. Their massive explosions released heavy elements, enabling new metal-rich star systems. Stars heavier than 250 times the Sun's mass collapsed into supermassive black holes, dominating space with gravity. Population 3 stars, as these first ones are called, were metal-free and extremely massive, with simulations suggesting they played a crucial role in reionizing the universe, stripping electrons from neutral hydrogen and allowing light to travel freely. Conversely, stars like the Sun take 50 million years to mature into main-sequence stars because the universe is cooler now. Clouds need less mass to birth stars. If a cloud's mass exceeds 13 times the Sun's or equals 0.08 times, it forms a brown dwarf, an object between a star and a planet that fuses deuterium but not hydrogen into helium. These are not true stars. From 0.075 to 0.5 times the Sun's mass, red dwarfs, the most common, comprising 70% of stars near the Sun, with surface temperatures from 1700 to 3300 degrees Celsius, cool and reddish. Next, orange dwarfs, 0.45 to 0.8 times the Sun, 2006 to 4900 degrees Celsius. Red, orange, and yellow dwarfs like the Sun are stable and excellent for nurturing life due to long cycles lasting tens of billions of years for red dwarfs. Heavier stars, type F, 1.4 times the Sun, white-yellow, 5700 to 7300 degrees Celsius. Type A, 1.4 to 2.1 times, 7003 to 9700 degrees Celsius. Type B, 2 to 16 times, 10,000 to 30,000 degrees Celsius. Type O, 16 to 90 times or more, 30 to 50,000 degrees Celsius, shining a million times brighter than the Sun. For every 10 million stars in the Milky Way, about 20,000 are type O, young and metal poor. All main-sequence stars fuse hydrogen into helium in their cores, the most stable phase. The Hertzsprung-Russell diagram classifies these, showing evolutionary tracks from birth on the pre-main sequence to the main sequence band. Red giants exhaust hydrogen, swell, become unstable, and change colors. Most first stars exploded or became black holes. Today, small stars become white dwarfs, then black dwarfs quietly. Large stars explode into neutron stars or black holes. Small stars live peacefully and die gently. Giant stars live brilliantly and die spectacularly. Which would you choose? Long-lasting peace or brief glory? Evolutionary models predict that in trillions of years, as the universe cools further, star formation will cease, leaving only stellar remnants in an era of eternal darkness. From ancient times, humans placed themselves at the universe's center, believing Earth life was rare and unique. But science erodes this view. Every creature contains intricate bonds, Earth is ordinary, and human intelligence is minuscule before the cosmos. We do not know our ancestors' origins, whether life seeds came from comets or meteorites, if the universe has controlling superspecies, or when we will find other civilizations. Exoplanet surveys from the James Webb Space Telescope in 2025 have identified over 5,000 confirmed exoplanets, many in habitable zones. Stephen Hawking was obsessed with extraterrestrials. He thought they were not rare, possibly nomadic on massive ships, conquering like Columbus. Statistics: billions of habitable planets, per updated Kepler and TESS missions, with TESS alone discovering thousands more candidates. They would be advanced, with power beyond imagination. Hawking warned that sending signals is risky. The probability of civilizations existing is high, but intentions are unpredictable. The universe is 14 billion years old, humanity 200,000 years. The Milky Way holds potential for life, with estimates of up to 100 million habitable worlds. But light speed limits us. Earth signals have reached only 100 light-years. It would take millions of years for them to arrive. If they come, faster than light travel, robots, million-year lifespans, or generational ships. Likely quantum robots, superintelligences, Earth as tempting prey. The Fermi paradox questions why we see no evidence despite high odds, with solutions ranging from rare intelligence to self-destruction or zoo hypothesis where advanced civilizations observe without interfering. Extraterrestrials might explain ancient mysteries. Egyptian pyramids. Built 4,000 years ago, 3 pyramids align with Orion's belt stars, 50-ton stones fitted seamlessly, transport mysterious, internal temperature 20 degrees Celsius preserving meat for weeks, positioned at equator meridian intersection more accurately than Greenwich, north alignment offset by Earth's motion. Mass 2 million tons, 18 times Earth's mass, base perimeter 18 times Sun's radius. Hidden messages. Coincidence or alien aid? Archaeological studies confirm precise astronomy, but construction methods involve ramps and levers, though some speculate advanced tech. Black night, photos from the 1950s, perhaps debris, but many believe alien ship. If a ship, it must be large for distant journeys. Recent space junk analyses debunk it as thermal blanket from a mission, yet conspiracy theories persist. The universe is mysterious, spiritual, extraterrestrials evident when someone says, "I created the universe," gifted for exploration. Quantum mechanics and cosmology intersect in theories like multiverse, where infinite universes exist with varying laws. Time is abstract, unreal, or human-made. In physics, relative, not absolute. Each day 24 hours equal, but rich-poor differ. Surveys, 75% believe future created second by second, 25% predetermined. Both true, depending on belief. Déjà vu, prophetic dreams prove predestination. Future flows forward but uncertain like Schrodinger's cat, alive dead until observed. Quantum entanglement suggests non-local connections, challenging classical time. Thoughts determine actions, future. Habits repeat create scripts. Master by living today, toward goodness. After 6:30 in the evening, life changes unexpectedly. The universe, time destroys all. Gravity shapes spheres, pulls centers. Stars, plasma, cause compress transform elements. Stellar nucleosynthesis forges elements up to iron, beyond requires supernovae. Stars live, fusion pushes out, gravity pulls in, balance main sequence. Exhaust hydrogen, helium, carbon, oxygen, neon, silicon, times decrease exponentially. 10 million years hydrogen, 2 million helium, 2000 carbon, 3 weeks silicon, seconds iron. Iron absorbs heat, core cools, gravity crushes, supernova. Core collapse supernovae leave neutron stars or black holes, enriching interstellar medium with heavy elements. Small stars, white dwarfs cool to black dwarfs, silent. The Sun, 5 billion years more swells, flickers, extinguishes, likely becoming a white dwarf after shedding layers. Binary systems, white dwarf accretes companion, exceeds 1.4 sun masses, type Ia supernova, standard candles measuring distances, confirming accelerating expansion. History, Homo sapiens 200,000 years East Africa, records 5,000 years. 98% before, mystery. Ancient myths like Sumerian tablets describe cosmic events paralleling modern cosmology. Ancient cultures narrate creation. Science, Big Bang 14 billion years, expansion, stars, solar system, evolution over 4.5 billion years on Earth. Religion, Creator. Science explains not life's source. Abiogenesis theories suggest RNA world or hydrothermal vents. Panspermia proposes interstellar transfer. 3 life scenarios, rare unique, common everywhere, orchestrated, superspecies or God. Drake equation estimates communicative civilizations, from 1 to millions. Life begins carbon, water, energy. Perhaps meteorites carry, but origin? Laboratory experiments recreate amino acids under early Earth conditions. Which scenario do you believe? The question invites reflection on our place in this grand, evolving cosmos, where ongoing discoveries from telescopes and missions continue to expand our understanding and humble our perspective.